Good afternoon, my fellow panelists and audience. Today, in this Energy Week 2026, we are starting with this session on logistics, storage, and infrastructure. In energy, we have a producing unit, we have a transmission, and as a consumer. In traditional concepts, we had constant sources like our fossil fuels, and that source was either consumed directly or converted to another form of energy like electricity or steam, and then was consumed. Now, with the advent of low carbon fuels, we have seen that there are many kinds of sources which are coming. And there is a variation. Earlier, the variation was from the demand side only. Now the variation is from production side only also. So today's session becomes important because this deals with the storage of that energy. So I have a distinguished panel here which will be dealing with how to store that energy. That is the link. In logistics, that is the major link between the production and the consumer. So we will be starting with that, and also for the low carbon emission fuels, we have a panelist who will be dealing with how to optimize using these low carbon fuels like ethanol. The session will be 15 for 1 hour at a stretch, and each panelist will be given 15 minutes. And I'm sorry to inform there will be no question and answer session. And you can see in the format there is no time given for the moderator, but I am stealing into their time only. So without any further ado, I will request the first panelist, Mr. Ajay Dashore. He will be dealing with the storage in rock caverns. Dashore sir, please.
Good afternoon. Thank you, Mr. Joshi, for giving us the chance. The topic which I would be dealing is strategic storage caverns, which are the rock caverns in India. So this is one of the unique storage method which very few people in India are aware of. How do you do the crude storage below 80 meters below the surface of Earth? So underground strategic oil reserves in rock caverns for enhancing storage security. This is okay. We'll be dealing with construction and evolution of underground strategic reserves, like how this concept has come into the picture and what is the present state. How difficult is construction? How much time it takes, and what are the challenges which you come across into this? Then what do we do in the operations and maintenance of these caverns, and what is the impact on energy security? And what is India's future plans for building on these reserves in India? So starting with the basic concept, what is the SPR? Strategic Petroleum Reserves. These are the reserves of buffer stock which government agencies such as ISPRL, Indian Strategic Petroleum Reserves, or oil and gas companies, which are both public and private, they have, in case of emergency, it can be utilized. Whenever there is a supply or a change, disruption, like if the supply is blocked in any of the Gulf state or any of your supplies are stopped. So what do we do for running your refineries? So in that scenario, it is these stocks which are buffer, which have been created, like these are your gold, black gold, I would say. You can draw from it and utilize into this. This is basically to provide economic and national security during an energy crisis. With the current geopolitical situation, like during the Ukraine war, You would recall the crude prices has gone till $120 a barrel at one time it surged. So it was those strategic reserves in which we dipped in, and US also released it and we also released from our sides, which had a dampening effect little on those, the countries are utilizing from there. So it is one of those things which you keep in your pocket for using in this. So presently what we have around 5.33 million metric ton, which is approximately 39 million barrels of crude oils, which we have at the three sites in country, which is Bangalore, Visakhapatnam, and Padur. So these three locations which have these underground reserves. Now to give you an idea of how does it look like a cavern, this is one of the pictures which was taken during the construction. You can see there's a date stamp time, 23rd December 2013. So this is a rock cavern which is 80 meters below the surface of Earth, and this is a gallery almost 700 meter long. So these are long tunnels which are unlined. There is no steel lining or any concrete lining over here. It's into these caverns which are man-made, like these are built from drill and blast technique. Controlled blasting is done of that. So total tunneling, we have around 35 kilometers of tunneling in which we store the crude. And the size is like length and width. Height is around 30 meters, which is almost 10-story building, equivalent to 10-story building, and width is 20 meters. So you can say why we do not use a tunnel boring machines, TBM, into this. So they don't have that much capacity to create. It is all maximum 5 meters width, whereas we have around 20 meter in width. So this picture was just before commissioning. The cavern was almost completely ready. It was taken because once you fill with crude oil, nobody can enter into this. It is sealed. So the only way is there are submersible pumps through which you take out the crude or. So as I was saying, how did this concept start? This was during 1973 Arab-Israel war, when there was an oil embargo on the US and other supporters of Israel by OPEC, like you could not use those crude. So this was followed by production cut, and there was an acute shortage of oil created during this and global price hike. So what was this done was that US embarked on this to create a strategic reserves. So on those lines, they had salt caverns in their place, old salt caverns in which they could utilize. But India didn't have any such thing. In 2004, like Government of India decided that we should also go and create for this strategic caverns. So this was when IEA was formed, International Energy Agency, and in that the countries which are the member countries, they have the strategic reserves which they can use. So now this, you can see it was an offshoot from that Arab-Israel war. This was created in 1974 to hold a collective response to major disruptions in the supply. Presently, there are 31 countries, and India is not a full-time member. It is an associate member since March 2017. So there is a norm that to become a member, you should have at least 90 days of crude oil product reserves equivalent of the previous year's net imports, to which government can have an immediate access. India has presently around 74 days of net capacity. This includes 10 days, 9.5 days of strategic reserves with ISPL, and net rest is with your refineries and national oil companies. So these are the three locations where we have these strategic reserves. Like Visakhapatnam, we have 2 caverns, totaling capacity of 1.33 million metric tons. Padur we have, which is, Udupi district. There we have 2.5 million metric ton. and Mangalore, it is 1.5 million metric ton. So it is almost 5.33 million metric ton, which is our national oil company's one-fourth year of production. Like ONGC has a production of 22 million metric ton approximately, so it's almost one-fourth of that, 5.33 million metric ton. So now the question is, how does these three locations provide in case of emergency to your refineries? So either they should be connected by pipeline or through sea. That is the only route. So the Mangalore and Padur, these are connected through pipeline to MRPL. Like we can directly take out the crude from these caverns and push it into the MRPL refinery, whereas in Visakhapatnam, we can give it to HPCL. Otherwise, then there are SPM through tanker loading, you can take out to the other refineries in Gujarat or other Bombay. So that's the way you utilize the crude onto this. So this is the typical picture of a underground rock cavern which is built below the earth. So you can see, creating this, you have to create various benches. Heading is done because you cannot do a total 30 meter in one go. So you had to create benches. So these are the cross section of benches, like it varies between 7 and 8 meters. The total height which I said, it is almost 30 meter into this. Now what are the advantages of rock caverns? As you know, we have said that this can be used as a buffer or strategic alternatives. These are safe from sabotage or natural calamity. Why? Because they are almost 80 meters below the surface of Earth. So even if bomb drops or missile drops, it is not going to affect any of these caverns. Environmental friendly, because you don't need a overground space, which is there, the requirement is minimum, and you can utilize it. Minimal land requirement, it is underground. There's no risk of leakage. Like in a steel tank or conventional tanks, you do need to carry out a regular inspection. Then testing and maintenance is required. In this case, since there is no metallic or steel structure is there, it is not required. Once you commission it, it is sealed off, and you just need to recirculate and maintain the hydrostatic pressure, which I'll come into this. It is a longer life, almost 60 years conventional life compared to this. Now, what are the challenges? The constructing them is a big challenge, because when you build an underground at this depth, you would encounter various rock stratas, which you need to check on their porosity, what is the quality of the mass, rock mass, over depth, weathering, shear zones. So these all need to be covered, and a detailed feasibility studies is done, and geotechnical maps are prepared. Based on that, monitoring, the site is chosen, and there it is constructed. So this is the biggest challenge. And while construction also, like, there could be water seepages, there could be wedge failures, there could be rock faults. So it takes almost 6 to 7 years for construction of each cavern. We started here in India almost 2008, 2009 construction, and it was completed and commissioned in 2016, one of the caverns, then 17, 18, like that. So this is what I was saying, water seepage in underground caverns. You can see the picture, how aquifers are coming while constructing. The laborers are standing over there, and then you have to control this, and then plug in and then take out the water. That's the challenging thing. The amount of rock debris, you can see around 22 million metric ton of rock debris was excavated during construction. So this is another challenge. You have to bring all this rock from 80 meters below. So this is a big logistic challenge, and it's almost, you can see a mountain of rock created at the site, which is still there at those sites, and disposing them off is a big challenge, plus bringing out from the cavern. This is two pictures which were taken during the construction phase. Like, you do a rock bolting. Rock bolting is you insert the bolts and rock while construction of caverns. So any loose portion, it does not fall down. It holds it. So you need to put various rock bolts. And the right side you can see is the one which is the phasing, which you see in the benching, no? So in phases, it is done. This is a picture of access tunnel through which you send all your equipment and machinery below the depth where your actual excavation is done. So the important thing here is what is the principle of storage in strategic reserves. So basically it is hydrogeological containment. Now, what is this? You would say when the crude oil is stored over there in depth, there would be vapors forming and these would seep out from the fissures in the caverns. So here we have a continuous hydrostatic pressure maintained over the cavern top, and that water continuously seeps inside and that balances, there is a vapor balance which is created. So it doesn't allow any vapors to seep out through the fissure. You can see this is a picture where crude oil is there, inert gas is there in the cavern, and outside you can see the blue, which is the water which is seeping inside the cavern. This maintains a pressure positive hydrostatic and doesn't let go the water hydrocarbon vapors outside the caverns. Thus, it is prevented from any hydrocarbon losses. This is a typical process scheme for strategic caverns. You can see a diagram like in inert gas, it is covered with that. Crude oil is there in the cavern section. And you can see the two pumps. One is seepage water pump and the other is for taking out the crude oil. And the water curtain is maintained, and the water which is taken out, it is recirculated in water treatment plant and again sent into the caverns or used for any purpose. So we have a zero discharge outside the plant in any of this. At the extreme top, you can see the crude tankers, which is connected through your SPM. And from here, it goes to either refinery or it can be sent directly to the caverns. This is the drill and blast followed by muck removal. So you can see you are putting the explosives in the rock by these drilling holes, and then a controlled blast is followed, and this method is basically used for your construction. So what we can say, these are the engineering marvels, largest in India, and total approximately 30 kilometers of tunneling. Padur itself is one of the things where 13.5 kilometers of tunneling have been done within 38 months. We have got our Padur site in charge, Mr. Yuvraj over here. Luckily, he has come over. And 86 kilometers of borehole and around 230,000 cubic meter of concrete and 84,000 cubic meters of shotcrete has been used. So next, what are our future plans? India has on annual already 2 more 6.5 MMT, and this would be first time on public-private partnership method, PPP method. So we have got in Chandikol in Odisha and Padur. And in this, they have been chosen. Right now, land acquisition is under process on this. So conclusion, I'd say just capacity is created, is not prone to any downtime due to maintenance and inspection. This is one of the major advantages of this. The cost of construction is almost 50% of the above ground facility. If you enhance the capacity, there would be only a marginal increase, and product storage is fully isolated. There is no chance of any fire or sabotage. So safety hazards on account of sabotage, storm is nil. Agriculture use, land is not lost, and surface land requirement is very low. These are, finally, I would like to conclude with this. These are perfect example of parallel underground spaces created without disturbing the above ground space. And this can contribute immensely to creating huge reserves of crude oil in a country that has huge importance. So this is, right now, our MRPL and HPCL, instead of creating the new storage tanks, they are taken these capacities on lease, and that's the way refineries are utilizing, and we are utilizing this. Thank you very much.
Thank you, Mr. Dashore. for your comprehensive presentation on rock caverns. You covered everything from construction to utilization, how it is transported. And after your presentation, I am feeling more secure. Rather, that at least for 9.5 days, we are secure, even if there is no supplies. So now, the next topic is regarding, again, storage. It is being presented by Mr. Gaurav Kumar, R&D Manager from Siemens. Please, Gaurav ji, stage is all yours.
Hello, good evening everyone. And first of all, I have to say that this is my first time in Goa informals. Thank you ONGC and thank you for the organizers here. I'm representing Siemens Energy and my topic is on compressed air energy storage. And in this, what we see around us every day, we are seeing the effects of globalization, we are seeing the demographic changes, we are seeing climate change, we are seeing digitalization, and then these things, what are they doing? They are drastically changing our environment. These things you must have been hearing in most of the conventions, most of the, in fact, daily news, but still, I always start with this only, that because I want these things to imbibe in our minds that yes, even if it's not visible, but these things are happening all around us. What does it create? Like, it creates the requirement for renewable energies. Now, in our company, there is a division with a transition of industry, where normally if I ask anyone that what do you understand by transition, he says transition means change from fossil to renewable. But actually transition is in the way energy is produced, in the way energy is stored, and then eventually in the way energy is consumed. But of course, in the layman's language, energy transitions means that we have to reduce our dependency on the fossil fuel-based energy, and we have to imbibe more and more renewable energy. The problem with this is that fossil fuel energy, you know what to do. If you have to increase the power output, you have to burn more fossil. If you have to reduce it, you have to reduce the amount of fossil. What to do with the renewable? For renewable, definitely, as we are increasing its penetration into the energy domain, the storage is a big question. And storage also in the long duration. Like, what are the solutions for the long duration energy storage? Of course, by 2030, most of the European countries will be looking at 50% renewable penetration. India is also looking at, like, by 2050, 100% shift on renewables. So how the storage system is going to look like? The problem also is that storage has to be available 24/7, and it has to be an integral part of the transition way of energy. So the solution that we are showing is based on this study. This study demonstrates on the y-axis you see it's the annual average discharge duration, and on the x-axis you see how the penetration of renewable energy is increasing. If we see that by 2050, most of the countries are going to increase their renewable penetration between 50% and 70%. And at this stage, then storage is a problem that they are looking at. When this comes, that 50 to 70% penetration has been done, at that time, the long duration energy storage, like more than 8 hours, it becomes really viable, cost viable also. Currently, if you ask us what is the cost viability of compressed energy storage that I am demonstrating here, it's very, very costly. But on this cost part, of course, we can talk later. What solutions currently Siemens Energy is having in the energy storage starts from very few microseconds and it goes up to days. In the microseconds, you can see that we have supercapacitors, some grid stabilizers, and then in the medium way, we have this compressed energy storage, redox batteries, and we talk about the complete energy transition where we are talking about the hydrogen economy, then it goes up to weeks of energy discharge. My topic today is this compressed energy storage. Looks very simple into its principle, Whenever we have this energy surplus, whether it's coming from what we are taking from the grid but not utilizing fully, and whether we are generating it through the wind power or from the solar power. This excess energy, what we do, we run a motor, we run a compressor with it, we compress the energy, and then we store it. We can store it in the caverns. Thank you, sir. Because you also concluded that more and more caverns should be built. I didn't know about your content, but then just related to it that yes, more and more caverns are needed, and they can be on above ground also based on the above total storage requirement. But of course, when we are talking about 10 megawatt hours, then I give you an idea that for 10 megawatt hours, nearly 2200 meter cube of the air is required. You can understand the volume. If I put it above ground, how will it look like? If I get a cavern, how beautiful the solution can be. And then when this energy is required, then I can run this pressurized air through a air turbine. It's running on air. That's why we see that there are no NOx or carbon emissions. The solution is very clean. Yeah. So here we are having two types of solutions in compressed energy storage. First one is this, what we call decaf. And the second one is adiabatic compressed energy storage. These are the two solutions which cater to two different sweet spots of the customers. In the first one, the difference is what am I doing with the heat that is generated when the air is compressed. When the air is compressed up to 70 bar, up to 100 bar, or up to 150 and 200 bar, tremendous amount of heat is generated. If I am letting it go to the environment, and then when I am extracting the energy from this compressed air, I have to preheat it before it enters the expander. At that time, I need this heat, which in the case of decaf solution, I am using it by fuel or by hydrogen. So this is more or less a gas turbine, but cut into half, where the compressed part I have utilized for the first half of the cycle, for the compression cycle, and the remainder expander I am using for the expansion cycle. In the ACAS, I am utilizing that heat which was generated during the compression. I am storing it. I can store it into the thermic oil. I can store it into the molten salt. And then when the heat is required to preheat the air before it enters the expander, I can use the same heat. Of course, the solution becomes more efficient, but more costly also because of this heat storage feature which gets added to it. This particular solution is up to 10 megawatt of hour, which we designed for our decentralized India location. So in this you can see that I'm storing this compressed air in these steel tanks, above ground steel tanks, and that's why for even a small megawatt of hour solution, the number of tanks becomes huge because there is a size requirement on the capacity of the steel tanks. We are looking at the options where these tanks can be replaced by concrete tanks, and whether they can be replaced by the glass fiber reinforced polymer also. Discussions are on. As soon as we have a solution, we will have that option also. So these compressors, these expanders, all in-between components are coming from Siemens portfolio with their proven technology, proven record. Some of these expanders and compressors, 20 years is a normal life cycle for these components. But for some of the markets, the same components with minor modifications, we have enhanced their life up to 40 years also. And as I said, that the solution goes up to utility scale, up to 300 megawatt of hour solution is available in case the caverns are available, because higher megawatt solutions are cost beneficial only when the caverns are available. Then these are the benefits. It responds very quickly. The compression can be achieved within 10 minutes. Flexible cycle options. full compression in 5 minutes, and because of these big rotating components, I have the inertia also, and it can store energy up to days of discharge. Like one of the running example is from USA, Alabama, where the discharge duration is 26 hours, and it is like capacity is 110 megawatt, and the discharge duration is 26 hours. So these are the characteristics, like round of efficiency with as like I'm representing the research and development team, and continuously we are working on our products, improving their efficiency. In this CAES complete cycle, now we are quoting the efficiency maximum up to 70%. And solutions from as low as 5 megawatt, it's written 50 megawatt here, but actually 5 megawatt, from 5 megawatt to 3 megawatt are available. Of course, in the expanders as well as compression cycles, I have to introduce more and more trains looking at the exact customer's requirement. Then there are zero greenhouse emissions. It's completely running on air. In the case of adiabatic, there is zero carbon emission, zero NOx emission. 10,000 cycles, they normally comprise up to 20 years of life, but as I said that up to 40 years now we are claiming. In the last, I will say the black start capability. More and more customers who are looking to venture into this compressed energy storage, they ask us this question, whether do you have a black start and whether you can prove it or not. So in the CAES, there are two running projects, Huntorf in Germany and Alabama in USA. This Huntorf facility is for 290 megawatt. Its discharge time is little less, up to 16 hours only. It was started during the World War II in Germany, and its sole purpose was only for black start. When everything is gone, then how will the power come back? So it has served its purpose, and now after 1979, it was converted into the completely compressed energy storage based power plant. For cost purpose, I will say that these two are the ones which are running. They are already making profit. In China, this market is opening up rapidly. Around 9 projects in this compressed energy storage are in different cycle of execution there. And when we talk about the cost there, like what is the cost, then China being China, that not enough information is out. But what information is out, that China is not looking at the cost. It is just installing. And based on these two projects, which Siemens Energy has, this Huntorf and Alabama, the plants have already started being profitable. The main problem which the customer faces is the capex. Like when he looks at the solution, he wants the return as soon as possible, minimum 5 to 7 years. But in this case, what currently we have calculated is definitely not in that direction. But by 2030, the compressed energy storage is going to be in comparison with the hydro energy storage. So like that's the target where we are working on, and we are marketing this technology in various festivals, looking for a venture, looking for the policies from the government also, so that we can execute one order in India. From the presentation earlier to me, based on this cavern, and I am very interested in the next speaker's topic also, where about some salt caverns we will hear. Those are like very much an integral part of this compressed energy solutions if you are talking about more than 100 megawatt of our energy storage. Yeah, that was my part. Thank you.
Thank you so much, Gaurav Saab, for sticking to the timelines, sparing some time for other speakers also. And with each speaker, my anxiety levels are going down. Now you have told us, we had an anxiety that this power is being produced from solar, wind. These are not constant sources. So how will you store? So now the solutions are there, and by the time 2030 will be ready with air compressors also. So now I am inviting Mr. Dr. Altaf Usmani to dwell upon the topic of rock cavern and salt caverns. So he'll be dwelling on that topic, please. Usmani sir.
Okay, a very good afternoon to everyone. And I think the first two speakers have made my work a bit easier. So at least you are aware what is underground. But what we are going to see in my presentation, it will be something new to everyone, maybe some new technologies, partly which is available globally and partly it is working in India. So I will just go quickly through this. So I am representing Engineers India Limited, the company which started this underground storage journey in the back 90s when the government of India took this initiative of storing the underground energy storages. So we move on from the starting of the rock caverns for crude oil, then slowly we have to go other sites. And very recently we completed the first largest LPG underground storage in India for HPCL. So coming to this journey, starting from the crude oil, we move to the LPG. And the latest one, what we are going to add as part of our India. So now we are going to add two new technologies. One of the technology is existing across out of the India, and the other technology is globally not existing at only one or two locations, and India will be taking up those initiatives. So in this journey, we have worked for a lot of products. Earlier, we have worked for crude oil, LPG, and now we are planning to have for natural gas, hydrogen, and other products also. So I think seeing is believing. So this you can see, this is the wonders our country has made. The largest crude oil cavern and one of the largest LPG cavern. So you can see as high as 31-meter high, a 10-story building, 20-meter wide, where the actual crude oil will be stored, a kilometer long, and another, the recently completed largest LPG storage, almost 80,000 metric ton. And the best beauty was that HPCL constructed this facility as part of the additional storage. So I will come back to the next slide. So this is the most innovation which we have done in India, which very few countries have done in the world. We don't use extra land, we don't use extra space. So there is no cost for extra land. You can see the spheres on one side. So these are the existing storage facility, and just for the capacity enhancement, we selected the same site, developed the same site for underground storage. So you have the surface storage and you have the underground storage. With the capacity of this is 80,000 metric ton. The total capacity at the surface is just 12 to 18,000 tons. So they have a huge capacity increment by this, making this underground storage within the same land. So the cost of land cuts down. Now coming to one more new idea, depending upon the requirements of the client, now we are coming up with a new technology where client requirements has you have different products and you want to store at one side. Suppose you have butane, you have propane, you have crude oil, you have diesel, and all storages you want at one side. So EIL is working on a technology where different products can be stored at the same site, same location, and you can use them independently. So this is one of the development we are working for our clients. Now, introducing you the first very technology globally existing only at one location that we call as lined rock caverns. Till now what you heard was a kind of a unlined. But remember that when we are trying to do unlined, which is based on the hydraulic confinement principle, you are going to store only low pressure products like crude oil or LPG, which are stored at maybe 2 bar or maximum 10 bars. But here we are trying to work for gas, for products which are up to 200 bar or 250 bars. So there that unlined system don't work, and we have developed this technology which we call as lined rock cavern. You can see this is a very simple system, but globally it is just picking up the pace. You have a kind of a steel liner inside for containment. You have a concrete block, and finally you have the rock. So all the pressure will be transferred to the rock, and this will be used for multi-product high pressure storage requirements. So this concept EIL is right now working, and very soon we will see some of the projects coming in this kind of lined rock caverns, a new conceptual development. And this will be used especially for natural gas and hydrogen storages. Just a view, this will be a kind of a shell, steel shell, which is protected inside the rocks from any kind of external threats. So that kind of system, depending upon the global requirements and present geopolitical situations, this concept is very much influencing all over India, globally, in the Gulf regions also. So for the shortage of time, I have to move quickly. Just this is the glimpse of how it is made. You have a steel shell, you have a concrete lining, and finally you have the rock. So steel shell will not work any purpose except containment. Everything will be controlled by the rock. So instead of a unlined principle where the water is used, we are using a steel shell for higher pressure requirements. So that's where this concept works. Coming to the another advanced technology which is available worldwide, not in India. In India also very soon you will see these kind of products which is called as leached salt caverns. In India, the availability of rock salt or halite, what we call as, is very limited to few locations. But whatever the locations we have, we are trying to convert it into an underground storage. The best part with this rock salt is that it is naturally impermeable. Whatever you put, it will remain as it is. And the other best part is that there is no blasting involved. Everything is controlled from the surface. You can do everything from the top. You can put the water will leach out the salt, and it will be a natural cavity where you can store enormous large volume of products. So that's what we call the leached salt cavern technology. This is the way how it works. You are putting the water from the top, you are leaching it out, you are making the cavity, and naturally it is storing any product up to a pressure of 100 to 120 bars. The only limitation is that availability of rock salt. Now, once you leach out the product, lot of salt is generated, which you can make evaporation ponds, you can evaporate it, and later on it can be sold commercially also. And the best part is that you can make lot of caverns back to back for storing large products within the same location, and these can be placed nearby, and you can store different products inside it. In US and Europe, this is very common, but India, we will be seeing very soon this kind of technology. Coming to some of the advantages and disadvantages on these two technologies, like both salt caverns and line rock caverns can be worked for different kind of products. The pressure range you can see, it varies from 100 to 200 bar. In case of line rock caverns, you can go up to 300 bars also. In case of hydrogen and natural gas, you can have different products in this one. The one that sir was discussing, CAES also, compressed air ones. You have the only requirement in salt cavern, as I told you, it was the salt formations. But in line rock cavern, there is no requirement. You can make it in a soil, you can make it in a weathered rock, you can make it in a rock. The pressure mechanism will be controlled accordingly. The best part is, this is impermeable steel lining, so there is no chances of leaking because steel is the containment part and the pressure part is the rock or the soil. There is a fast injection, the high flexibility, the geology, this part, there is no dependency on geology because you can make in different kind of rocks depending upon the location. The capital cost, that is one question, but as I told you, the cost is governed by the land, real estate land. If you have the availability of land, you can use it for the dual purpose. You can have the surface facilities and also you can have the underground facilities, so the cost of the project can come down. Commercial readiness, as I told you, this salt caverns are widely available US, Europe. The line rock cavern technology, it's only one available in Sweden, and I believe next one will be the India in the world. And coming to the cost implication, yes, salt, because we are not going inside, not doing anything, everything is controlled from the surface. You have a lower capex cost, but in terms of LRC, the cost is high, but we are working on a system where this can be compensated by large volumes, low land cost, and wider geographical applicability. So these three factors can impact your cost calculations. Coming to conclusions, we can see salt caverns ideal in regions which are thick, which have the formations. The LRC is available in both soft and hard rock. Lower cost in terms of salt caverns, and salt caverns have large storage capacities. LRCs, you have you can put it anywhere near your demand center and ports. LRC's salt cavern best part, they are the naturally healing part. You can store it because of the impermeable nature. LRCs are engineered. You can engineer them as per your product requirement, as per your pressure requirement. In LRC caverns, you have the steel concrete as the lining. And the best part, the multi-product storage. This new system we are coming for clients where you have different products at one location. So both in unlined and lined rock caverns, you can make this technology. So salt caverns and LRC both offer universality, and together they form the backbone of any underground storage future of the country, and definitely for India also. To appreciate this is a small video on the journey so that you can appreciate more on the work we have done so far.
Oil price volatility and supply disruptions necessitate robust strategic measures. Recognizing this, the Government of India envisioned a strategic petroleum reserve program to safeguard the nation against energy contingencies. EIL has played a pivotal role in this initiative since its inception, overseeing the conceptualization, design, and execution of India's strategic crude oil reserves. Under Phase 1, EIL successfully delivered underground rock cavern storage projects at Visakhapatnam, Mangaluru, and Padur, with a combined capacity of 5 million metric tons. Underground unlined rock caverns are an advanced and proven storage solution. This technology employs groundwater pressure to securely contain hydrocarbons. Each facility features interconnected caverns, vertical shafts, and sloping floors that ensure efficient oil flow and vapor pressure control. The design is rooted in meticulous geological investigations, ensuring both stability and safety. In addition to crude oil storage, EIL has achieved a landmark feat with India's largest LPG storage facility in Mangalore. This 80,000 MT rock cavern project exemplifies EIL's engineering excellence, navigating complex challenges and enhancing energy storage capacity. Looking ahead, EIL is expanding its expertise to align with India's integrated energy policy. From Phase 2, crude oil reserves, to pioneering new designs for pressurized hydrogen and natural gas storage, EIL continues to innovate for a sustainable future. With accolades like the National Geoscience Award and groundbreaking contributions to underground storage technologies, Engineers India Limited is not just building energy infrastructure. It is building resilience, sustainability, and a brighter tomorrow for over 1 billion people.
Thank you very much. Okay.
Thank you, Dr. Usmani, for sticking to the time and also opening up the discussion from rock caverns to salt caverns. So further opening up the discussion, now this energy is when it is transformed to electricity. So we have Mr. Yadav from Power Grid who will be telling us about electricity storage. Yadav sir, please.
Good evening, sir. Actually, if you come to know that total energy generation is green energy generation is 265 megawatt today. On governments of India ambitious plan is about 500 gigawatt by 2030 and 620 gigawatt by 2032 and about 1800 gigawatt by 2047. Right now, the problem is not the generation. The problem is the storage. Presently, we are using the pumped hydro storage and lithium-ion energy storage system. But this is the for short time duration. For long time duration, we need to shift the technology like advanced energy, air compressed energy storage system, or iron redox, flow battery. So we are here. India aim for 500 gigawatt of non-fossil fuel capacity by 2030, requiring significant increase in solar and wind power generation. This introduces variability, creating challenges in managing the Duke curve. Duke curve is the basically the difference in generation and utilization. Generation, green hydro generation is, green hydrogen or solar is generated during the midday time, generally 11 hours to 15 hours. But the load is generally from morning to evening, morning hours and evening, morning load and evening load. So manage that thing, energy storage is very much required. Present limitation of current energy storage, pumped hydro storage is geographically constant and lithium ion battery economically degrade linearly with the duration. Achieving net zero grid requires technology capability of 8 to 12 hours of discharge. So need for innovation solution, achieving net zero grid requires new storage technology offering 8 to 12 hour discharge for flexibility, reliability and cost effectiveness. Promising long duration energy storage. The paper explores advanced compressed air energy storage, iron redox, flow batteries, and high density thermal energy storage as potential solution to bridge the evening peak. Synchronizing grid benefit for long duration energy storage. Long duration energy storage can reduce renewable curtailment by 18%. Actually, the generation, when the peak generation is there, basically solar, then in the peak hours we have to curtail the generation, because there is no provision available for the storage of the energy. So by storing long duration energy storage capability, we can curtail the generation by 18% and improve the grid stability by 7%. Further, we can reduce the requirement of new transmission line, which is generally 300 to 500 crores per gigawatt per year. Further, levelized cost of energy storage. The levelized cost of energy storage is a crossover point between 6 to 8 hours of discharge duration, where long duration energy storage technology demonstrate a lower LOS compared to lithium ion. Advanced compressed air energy is a promising long duration energy storage technology that utilizes synchronous motor generator to provide critical grid stability features such as physical inertia and short circuit strength. Geographically, advanced compressed energy storage aligns well with the high solar generation in the salt formation of Western India, particularly in the state of Rajasthan and Gujarat. As other panelists already told that this is this is more suitable where the more generation of solar generation is available. This is the pictorial diagram of compressed energy storage. The energy can be stored during peak generation and can be utilized during the peak demand, morning hours and evening hours. This is iron redox flow batteries diagram. In iron redox flow batteries use ferrous and ferric ion in redox reaction, enabling scalable energy capacity based on electrolyte volumes. Cost and storage efficiency. Redox flow batteries provides lower marginal storage cost than lithium ion for energy duration over 6 hours due to decoupled scaling. Safety and environmental benefit. There is advantage of safety as well as environmental benefit. This is non-flammable, non-toxic, electrolyte enhanced safety, making redox flow battery ideal for urban substation without thermal risk. Suitability for high density storage, long cycle life and safety makes iron redox batteries robust solution for India's high density energy storage demand. And this is thermal energy storage. Phase change material are used for the thermal energy storage, which is used for store thermal energy efficiently by changing states between solid and liquid. Steam turbine and electricity conversion. Stored heat is converted back to electricity through steam turbine, enabling efficient energy recovery. Retrofilling coal plant. Thermal energy storage can retrofill old coal plants by utilizing existing infrastructure like switchyards and transmission lines. Cost-effective grid integration. Thermal energy storage offers a cost-effective solution for long duration storage, minimizing new infrastructure need in the power grid. This is the comparative technical parameters. Lithium ion is suitable for 1 to 4 hours. Iron redox batteries are 6 to 12 hours, and advanced compressed air energy storage is 8 to 24 hours. Round trip efficiency for lithium ion is 85 to 95%. Redox flow battery it is 65 to 75%. Advanced air compressed energy 60 to 70%, and life cycle For lithium ion, it is 300 to 500 life discharge cycle. Iron redox batteries is 20,000 plus discharge cycle, and advanced compressed air energy storage is 10,000 plus cycle. Inertia, lithium ion storage battery is synthetic, provides synthetic inertia. Iron redox, it is synthetic inertia, and advanced air compress is a physical inertia. Fire risk for lithium ion is moderate. Iron redox is there is no risk of fire, and advanced compressed air energy, it is very low. And this is mitigation of renewable curtailment. This can be used for long duration energy storage potential. Investigating the strategic potential for long duration energy storage technology is basically advanced compressed air energy storage, iron redox flow batteries, and thermal energy storage for improving the resilience and reliability of India's power grid. Grid stability and inertia, advanced compressed air energy storage can provide essential ancillary services, fast response frequency regulation, and physical inertia. Critical for maintaining resilience in high variable renewable energy environment. Integrating synchronous based storage can improve local system inertia by approximately 7% during contingency events. Reducing renewable curtailment. Integrating a 10-hour duration, long duration energy storage assets can theoretically reduce annual renewable curtailment by up to 18% in renewable risk corridor by absorbing the broad belly of the solar generation curves and discharging during periods of high demand. Economic viability and transmission deferment can achieve cost parity with conventional peaker plant of the duration exceeding 8 hours, particularly transmission estimated at 500 crores per gigawatt year is factored into value stack, suggesting long duration energy can serve as a non-wire alternative to defer costly transmission upgrades. And this is the curtailment benefits. Renewable energy annual curtailment can be reduced by 18%. Grid stability will be improved by almost 7%. Economics, this will reduce the new cost of new transmission line, and assets life will be more. And this is cost efficiency of lithium ion is up to 4 hours. If you are using the discharge cycle of 4 hours, then lithium ion battery will be better. Long duration energy will be better for up to more than 8 hours of energy storage. Global benchmarking projects. Presently in Canada, advanced compressed energy is being used, and iron flow batteries are USA and Germany. Long duration energy storage is strategically important for modernizing India's power grid and ensuring energy reliability. This is barriers. What are the barriers to long duration energy storage? This is lack of market mechanism. Reform government introducing a stability market incentive for pilot programs is essential to encourage adoption of long duration energy storage. Collaborative efforts is required. Collaboration between transmission system providers and regulator through geologically mapping can unlock resource potential, and accelerating integration. These reforms of collaboration aim to accelerate long duration energy storage integration and improve grid reliability in India. Thank you.
Thank you so much, Mr. Jay Prakash Yadav, for sticking to the timelines and taking us through the electricity storage. Now, we have discussed a lot about the storage of energy. Why this was required? As in my opening remarks, I was telling, this is required because the production itself has become variable. And why variable? Because we are going for low carbon options. And in that option, I want to say that India has given a success story called ethanol. So we have been adding 20% ethanol in MS. And now, once the R&D stage, then implementation stage, once we implement the things, then we think about the optimization, how to do that in a more optimal way so that we can reduce the cost and increase efficiency. So our last speaker, Ms. Pratibha Chand, will be deliberating on a very important topic of EBMS optimization. Please, the stage is all yours.
Good evening, everyone. I'm Pratibha, and the topic of my presentation is EBMS based logistics optimization. So, before we go ahead, I would like to take you through the entire process of oil logistics framework of any oil marketing company, which begins with the crude procurement. And once the crude is procured, it is transferred to the refineries through coastal mode, through vessels. And once the refinery does the processing, the finished product is moved to the storage locations, which we call as terminals, through various modes of transportations like coastal vessels, pipelines, rail, and road. And from these terminals, the product is moved to smaller depots through rail and road. And from these depots, the product is moved to final outlets through tank trucks. This is our journey of the strategic initiative of the ethanol blending in MS, which has not only reduced our MS purchase but has also done its bit in contributing to the cleaner environment. The journey, as we can see, 9% blending in year 2021-22 to remarkably jumping to 16.7% in 2024-25. And now we have been able to achieve our target of 20% blending in the MS. Optimization. So, in a supply chain network which has got multiple nodes and branches, there are opportunities of optimization at various levels, right from product procurement to the logistics. And hence, a combination of both purchase and logistics plays an important role. How to decide which depot or terminal will be fed from which refinery, or which outlet will be fed from which terminal or depots, is all this optimization activity is all about that. For us, we categorize this into three types. Primary optimization, which decides that which terminal or depot will be fed from which refinery or import location. The secondary optimization we call is when we decide which outlet has to be fed from which terminal or depot. And then there is another type which we call end-to-end optimization. Here we optimize the entire network, right from refinery to the end customer, the outlet, in one single network via terminals and depots. This type of optimization is mostly suited for products which have less tax implications like LPG, which comes under GST, and there is no problem in moving product cross-state. But in products like MS and diesel, which have tax implications on moving the product out of state, we normally use primary and secondary optimization independently while using inputs of one in the other one. The optimization challenge: while carrying out these optimization activities, we come across certain challenges, or rather factors, which decide the entire optimization. The first one is the regional imbalance. Basically, the availability of product is not everywhere, whereas we have to cater to the demand of the entire country. So, basis the location of the refinery and terminals, we decide where the product has to come from. The next one is the price volatility. So, as we know that we have got limited refineries and limited terminals and depots, so definitely the price will be cheaper closer to the production side, which is the refinery. And as we move forward, the transportation cost will keep on adding to it, which will increase the prices. The third one is the complex logistics. So there are most of the places where we are able to place the product by pipeline or by rail, but then when we have to go to far off locations in northeast, etc., then we have to move the product through tank trucks, which adds to the cost. The traditional approach of the optimization, here we use the concept of least landed cost principle. This is represented by the minimum possible combination of all cost elements. So when I say cost elements, it includes the product purchase cost, the primary transportation cost, which is the refinery to terminal and depots, the secondary transportation cost, which is depots to retail outlets, then storage and handling charges, and then the applicable taxes and duties. When I'm saying the combined cost, that will take care of all the components put together. So they can be chances that there is a outlet which is close to say location A. So it can be a possibility that it may not be fed from this location A, but maybe fed from another location B, which is slightly far from the retail outlet compared to the location A, because we are taking all these components put together. Now here in EBMS innovation weighted cost structure, so in case of MS and diesel, in a state if we have got say more than one location, usually the price difference of both the locations is not much. It would be few hundreds or maybe maximum few thousands, because either both the locations would be supplied from the same original source, or even if they're not supplied from the same original source, the difference would not be much. But in case of ethanol, it is not the same, because the price of ethanol depends on the raw material and then where the distillery is. So it can be a possibility that in a state like Maharashtra, we have got say two locations, Nasik and Sholapur. It can be a possibility that Nasik is supplied by a distillery from Madhya Pradesh, which is using raw material of maize, or Sholapur is supplied by a distillery from Maharashtra itself, which is using a raw material like molasses. Now we know that there is a huge cost difference between the ethanol prices, which are supplied from molasses versus which are supplied from maize, which can go, the difference can go up to 12 to 13,000 per KL. So now if we talk about EBMS, ethanol part in MS, we know that there is a substantial component of ethanol in the final MS, which is supplied from the retail outlet, which is 20%. So we decided to use this weightage of this component in the final cost. So if we have a location which has lower MS placement cost but higher ethanol cost due to distillery location, and we have got location B which has got higher MS or diesel placement cost, but the ethanol price is lower. So in a traditional approach, we would have definitely gone with the location A, which was having lower MS and diesel cost. But if we want to give the weightage, bring the weightage of ethanol as well in the entire cost, we can see that the results may change. So what we did, we redefined the primary cost structure by incorporating the both MS and ethanol while calculating the cost of MS. We added, we gave weightage of 80% of MS cost and 20% of the ethanol cost. So finally, our landed cost became the summation of EBMS cost instead of MS, and then HSD purchase cost, and then as usual, the irrecoverable taxes, primary transportation cost, and secondary transportation cost. To our surprise, we actually witnessed there were some changes in the linkages which were proposed by the solution. Implementation challenges, though this exercise proved to be quite cost effective, but we faced certain operational challenges. The first one was the capacity constraint at locations. Though there was potential to realign many outlets, but we had constraint of capacities in handling products at our locations. So, and also the transportation handling capacity. So we could realign only a part of the outlets. The second part is ethanol availability. So now in certain sectors, the ethanol availability is restricted. If we want to move more product, more ethanol to a certain location, that will come with the baggage of the transportation cost, because ethanol is moved by trucks only. So then this moving more ethanol would have undermined our whole objective. The third challenge that we faced was the consortium arrangements. So there were cases when there was a potential to realign one outlet to a particular location B from location A, which had some consortium arrangement with other outlets which were not proposed to be realigned to location B. So in that case, we had to see the collective economics of all those outlets put together. And then accordingly, we had to decide whether they have to be retained at the location A or they have to go to the location B. So in conclusion, so there were measurable impact of the entire exercise. The exercise was cost effective, and we were able to carry out the optimization by reducing the cost of the entire logistics. We could do the dynamic balancing, because we have some minimum purchase requirement of the ethanol, whereas the demand of ethanol was based on MS, which kept on fluctuating basis the demand of the MS. And then strategic realignment, efficient outlet linkages shifts basis the MS ethanol economics combined were done. Scalability, if we talk about the exercise, yes, can be adaptable to other evolving blending targets and energy transition goals. And there are future opportunities. Right now, we have restriction in moving product cross state, but if MS and diesel come under GST, then we will be able to unlock additional benefits through the entire exercise. Thank you.
Thank you, Ms. Chand, for the wonderful presentation on optimization, making this look very simple. I know this process is very complex. However, your presentation showed it that it can be done, and you have proved it. So, in conclusion, I will say the theme of this session was logistics, infrastructure, and storage. Storage was in between, but most of the presentations were on storage. Logistics we touched upon in optimization, and also as it was explained that how the storages in the caverns is actually transmitted to the refineries and our locations. And infrastructure, we have seen massive infrastructure like 30 meters, 20 meters heights of rock caverns and salt caverns. So those infrastructure was widely covered. So it was a wonderful session for all of us, and I think with this session, a lot of queries regarding infrastructure, energy storage would have been solved, and if there are still some queries, you can always connect with the speakers and ask them about that. So thank you so much.